So again, to prove the Leibniz rule, when n is equal to 1, we basically just do the derivative of the whole function. So we do the derivative of this whole function, of the summation of the function and k f of x when n minus k g of x to the k. Okay, so basically we do the derivative of this function when n is equal to 1, and if we do that, we should be able to prove this function. So now when we do this, we will get by the way, when from k0 to n, now we should get is equal the sum from k is equal to 0 to n of 1 k f1 minus k of x g k of x. Okay, again, we're going to do the derivative of this function using the product rule, and this should give us 1 0 f of 1, again because we will replace 1 anywhere we have n. G of 0 plus 1 1, again 1 minus 1 is just going to be 0 of x g of 1 of x. So basically, as you can see, it's exactly as the product rule. Now from here we can just clean it up a little bit to make it more nicer. We can just use algebra to clean it up a little bit, but first we can use the factorial equation to solve for these values. And we know the factorial equation is just nk is equals to n factorial over k factorial multiplied by n minus k factorial. And when we use this formula for this value, this will become 1 and this will also become 1 if we just plug in these numbers. So both of this value will become 1, and when that happens, so now we're only left with f prime of x gx plus f of x g prime of x. And as you can see, this is exactly the product rule. This is exactly the same as this. You see? So that means using the Leibniz rule does give us a solution similar to the product rule. Okay, so now what happened if we can also do the same, we can go through the same process to see what happened when n is greater than 1. Okay, let's do that again.